Good afternoon. My name is KCollins, and this is my presentation on agricultural remote sensing advancements, applications, and future opportunities via a literature review. So, a brief introduction. So, agriculture is an imperative aspect of human life because food is critical to growth, development, and survival of human beings, as well as many other beings. So Weiss et al. Observed that an increased demand in feeding humanity coupled with climate change intensifies the need for sustainable practices, while those pressures associated with population increase, disease, climate change, and energy problems prompt emphasis on sustainable agricultural practices such as remote agricultural sensing. And then in addition to realizing environmental sustainability, the need to achieve maximum yield and optimize resource management over limited arable land spaces encourages the incorporation of effective tools such as remote agricultural sensing. So Hong et al. Define remote agricultural sensing as the technology utilizing sensing emission characteristics of target objects, so water, soil, crops, and their spectral reflectance, by applying physical media like heat and light. And this literature review presents an analysis on current research related to agricultural remote sensing, focusing on technological advancements, recent applications that are practical, and untapped opportunities for future exploration. So on this graphic here shows several of the uses for remote sensing technology. So seed spreading, crop analysis, smart data, gauging soil erosion rates, field monitoring water stress, and diagnosis of diseases, as well as, spread. So fundamental principles of remote agricultural sensing. So generally, remote sensing operates on the foundation principles of the electromagnetic spectrum and electromagnetic radiation. So EM radiation refers to the flow of energy in the form of electric and magnetic fields that make up the electromagnetic waves. In the context of agricultural components of the agricultural landscape, including soil, water, and crops, interact with electromagnetic radiation at various spectral signatures that inform the identification of the component status. And then the identification of those components under EM radiation is made possible by principle that the component's properties determine the wavelength and intensity of the radiation, which enables that differentiation of components. So what are some advancements in agricultural remote sensing? Optical sensing, so including hyperspectral and multispectral sensors, are preferable for vegetative sensing due to their higher sensitivity and properties involving vegetation. Hyperspectral sensors acquire data in multiple contiguous and narrow spectral bands. These provide more detailed spectral information on subtle changes in plants' biochemical constitution and health, while multispectral sensors acquire data in various spectral bands, making them preferable for obtaining vegetative indexes, so at EVI, NDVI, and atmospheric resistance vegetative index. Specifically, multispectral sensors are ideal for determining plant health since they aid in determining level of photosynthetic activity. Thermal sensing is another advancement, which thermal sensors operate within the thermal infrared region of the electromagnetic spectrum, detecting variations in surface temperature. And these sensors are really effective in monitoring changes in soil moisture, assessing potential water stress in crops, relying on those temperature differences to identify those conditions. As elevated surface temperatures recorded by these sensors can suggest reduced transpiration rates in plants, which can serve as an indicator for water deficiency and the need for irrigation. Microwave sensing that encompasses both active and passive types. So active sensors such as radar, which emit their own signals and measure that energy that's backscattered from the Earth's surface. Passive sensors detect naturally emitted thermal radiation within that microwave spectrum. These sensors are particularly advantageous in agricultural monitoring because they can penetrate vegetative canopies, cloud cover, and unfavorable weather conditions to reliably assess soil moisture levels. And then what are some agricultural remote sensing platforms? So at the broadest scale, these are the satellites are the preferred choice due to their ability to deliver a wide range of spectral, spatial, and temporal resolutions, enabling consistent monitoring across local, regional, and global levels. For a more targeted observation over smaller areas, aircraft often offer a reliable platform for capturing that high-resolution imagery. In recent years, that's going to be drones and other unmanned aerial vehicles, so UAVs. And those have gained prominence in remote sensing applications due to their affordability, operational flexibility, and sustainability for capturing that high-resolution data. So UAVs are increasingly being utilized in precision agriculture, where their ability to collect detailed on-demand data that can support site-specific management. So this capability enhances timely decision making, which is really a critical component of sustainable agricultural practices, and such as like pest or disease management. So what are some applications in agricultural remote sensing? So we can monitor soil moisture. So researchers, data collectors, farmers monitor this soil moisture through remote sensing, applying optical remote sensing to determine soil surface moisture. Depending on spectral reflectance within the near infrared band. For deeper level soil monitoring, microwave remote sensing is ideal because it detects both surface and root zone soil moisture, penetrating canopies and cloud cover to detect those properties. Incorporating the hydrological models coupled with remote sensing provides a comprehensive monitoring of soil moisture, supports drought forecasting based on soil water dynamics. Another application is predicting crop yield. So accurate crop yield prediction is essential because it informs critical decision making, such as storage logistics, crop insurance planning, harvesting scheduling, etc. Remote sensing plays a pivotal role in the yield forecasting through the integration of machine learning techniques, statistical regression approaches, and cross-group simulation models. And the use of UAVs in remote sensing enhances the precision of yield predictions, especially when combined with ground truth yield measurements for model training and validation. So given the variability in the relationship between vegetative indices and final crop yield across different seasons, it's crucial to identify the optimal growth stages and time periods to improve predictive accuracy of remote sensing based models. So another application is detecting plant diseases and pests. So early detection and mapping of plant diseases and pest infestations are vital for minimizing crop losses and implementing timely control measures. So remote sensing technologies can identify these threats at early stages by detecting subtle physiological and morphological changes in plants, which manifest as variations in spectral reflectance. So thermal sensors also contribute to disease and pest detection by monitoring changes in canopy temperature, as infected or stressed plants often exhibit elevated temperatures due to reduced respiration. So a notable limitation of remote sensing is its difficulty in distinguishing among different disease symptoms, though, and in separating plant stress caused by environmental factors from that caused by pathogens and pests. So assessing crop health and detecting stress is another application. So monitoring crop health and identifying stress conditions are key components of successful agricultural management, because this enables us to make those corrective actions and optimize yield. So vegetative indices such as NDVI, EVI, and ARVI are derived from hyperspectral and multispectral remote sensing data to evaluate plant vigor, chlorophyll content, photosynthetic content, biomass levels, etc. In addition to thermal infrared imagery, which is effective in detecting plant stress by measuring canopy temperature. Under stress conditions, plants often close their stomata to conserve water, leading to a decrease in transpiration and the corresponding rise in canopy temperature. So integrating AI and machine learning and remote sensing. So artificial intelligence and machine learning have become pivotal in the advancement and expanded use of remote sensing in agriculture. These are really powerful algorithmic tools to process and analyze large data sets. And these technologies allow researchers and farmers alike to extract valuable insights from this complex, extensive data, enabling rapid decision making and facilitating sustainable agricultural practices. AI enhances the accuracy and precision of crop health assessments, disease detection, and nutrient status evaluation, particularly when integrated with hyperspectral remote sensing data. So the combination of AI's analytical capabilities with this extensive spectral information provided by hyperspectral sensors enhances this precision agricultural monitoring and management. And as it continues to evolve, new algorithmic techniques such as deep learning and recurrent neural networks, or RNNs, are being introduced, as these innovations can be really beneficial in analyzing temporal sequences of remote sensing data, supporting agricultural tasks like yield prediction and crop growth monitoring. So what are some of the challenges, limitations, and future opportunities in agricultural remote sensing? While remote sensing presents significant opportunities for advancing sustainable agricultural uh, methods and measures, as it reduces, and minimizes the uh, usage while maximizing crop yields, several challenges persist. So one of the key obstacles is the adoption of remote sensing technology by farmers, because it often requires ongoing training, continuous tech support, more user-friendly tools, as well as the cost. And then interpreting the data from these remote sensing tools can be really complex, posing difficulties for farmers and agricultural professionals. While machine learning models can be trained to identify crop patterns indicative of pest infestations or diseases, differentiating between specific diseases and pests remains a challenge. So similarly, distinguishing plant stress from disease symptoms using remote sensing does remain difficult. Another limitation is the satellite-derived remote sensing metrics do not fully capture all of the factors influence crop production, limiting the ability to accurately interpret crop growth dynamics. On the other hand, remote sensing technology and knowledge continues to improve. So new opportunities are really emerging for its application in agriculture. Data has become increasingly a cornerstone for agricultural decision making. Farmers are, in the data market now. They're in the data science business, and this, helps enhance the resilience of agricultural systems while delivering these benefits for the environment, the climate, and local communities. So, continuous evolution of AI and deep learning technologies offer exciting prospects for more advanced machine learning and AI algorithms that can further enhance predictive models, feature extraction, and image analysis in agricultural. So improving data collection coupled with advancements in AI and machine learning will provide farmers with more accessible and effective tools that translate to remote sensing data in real time, giving them, those actionable solutions. So additionally, innovations in drone technology and UAVs, when combined with machine learning, are expected to really improve precision in crop monitoring and management, which continues to promise greater advances in agricultural practices in the future. So in conclusion, this literature reviewed some of the transformative roles of remote sensing technologies in modern agriculture, emphasizing the growing influence and reshaping of traditional farming practices. So significant advancements in satellite imaging, machine learning, artificial intelligence, and big data analytics allow remote sensing to evolve as from the theoretical concept into this really practical and powerful tool for agricultural innovation. So these technologies enable precise monitoring of crop health, soil conditions, water usage, weather patterns, and more, supporting informed decision making and resource optimization. So these technologies will continue to develop at the rapid pace they've been going, often in an interconnected and complementary manner. And so the potential for remote sensing to contribute to the realization of sustainable and resilient agricultural systems is increasingly apparent. The convergence of these digital innovations not only enhances productivity and efficiency, but also addresses these global challenges such as food scarcity, climate change adaptation, and environmental conservation. And consequently, the future of agricultural remote sensing appears exceptionally promising. It's poised to play a central role in the data transformation and the digital transformation of the agricultural system. And here are my resources. Thank you for watching.